Welcome back to the Explainer. Today we're zooming in on optical instruments. But we're not just going to talk about the glass lenses and circuit boards sitting on our desks. We're actually going to explore how the remarkable, living biology of our own eyes compares directly to the mechanical cameras we use every single day. It's pretty wild when you actually stop and think about it, right? Have you ever considered the sheer physics happening inside your head at this very second? As you sit there watching this Explainer, you are actively running an incredibly sophisticated biological machine. So the central question we're tackling today is, how exactly does nature's organic lens stack up against human engineering? Let's find out. All right, here's our roadmap for today. 1. The basics of optics. 2. Inside the human eye. 3. Common vision defects. 4. The mechanical lens camera. And finally, 5. Biology versus machine.
Let's kick things off with Section 1, the basics of optics, refraction and reflection.
Before we can really compare an eyeball to a camera, we need to lay down a quick foundation. Every single piece of optical tech operates on the exact same physical laws of refraction, which is just the bending of light, and reflection. Whether we're talking about precision glass lenses or mirrors inside high-powered telescopes, or, the organic tissue inside your head, they all share this core principle. Light comes in, and the instrument manipulates it. The only real difference is whether we're talking about a mechanical domain or a biological one. Moving right along to Section 2, inside the human eye, an organic optical system. Take a second to think about the incredible organic lens system you are actively using right now. The human eye is safely tucked away inside our skulls, securely held by this intricate web of muscles that seamlessly connect blood vessels and nerve cells. It's definitely not just some passive window to the world. It's a highly active, organic optical system. Every single component you're looking at here is precisely arranged to work in perfect harmony, all to capture and focus light. If we break down the front end of the eye, we find a seriously brilliant light control system. First up, light hits the cornea. And get this is a super surprising fact. That front protrusion, the cornea, actually provides twice the refractive power of the eye's internal lens itself. Right behind that is the aqueous humor, which is a liquid that holds the eyeball's shape while letting light pass right on through. Then you've got the iris, which elegantly expands and contracts to control how intense the incoming light is. Finally, the internal biological lens tags in, working with the ciliary muscle to adjust the focal length in a process called accommodation. So the crucial point here is that all this perfectly bent and focused light has to go somewhere, right? Its ultimate destination is the retina. This is the light-sensitive layer coating the entire back of your eye. This is where the biological image projection actually happens. And amazingly, the image projected onto your retina is completely real, but utterly upside down. It's totally inverted. Your brain actually does all the heavy lifting of flipping it right side up for you. Once that light passes through the vitreous humor and smacks into the retina, the real magic of sensory transmission begins. The retina is absolutely packed with specialized cells, cones, which handle daylight and color, and rods, which power our night vision. These cells basically translate light into electrical data, which is then fired down the optic nerve. That nerve? It's basically a massive biological cable containing over 1 million individual axons connecting straight into your brain. Interestingly, because all those nerve fibers have to bunch up and exit the eye at a single point, there's absolutely no room for sensory nerves right there. So you literally have a tiny blind spot in your vision that your brain just paints over. Kind of wild, right? Section 3. Common vision defects, when biology is imperfect. It's honestly amazing how simple the mechanical fix is for a biological shape issue. Take myopia, or short-sightedness. If you have this, things in the distance look super blurry because the eyeball itself is physically just a bit too long. The perfectly focused image lands in the empty space right in front of the retina instead of directly on it. To fix this, we literally just place a diverging, concave lens in front of the eye. This spreads the light out just a tiny bit before it enters, pushing that focal point perfectly back onto the retina where it belongs. Now, contrast that immediately with hypermetropia, which is long-sightedness. Here, objects up close are blurry. The cause is the exact opposite of myopia. The eyeball is physically too short, so the optical system is trying to project the focused image behind the retina, basically right through the back of your head. To correct this one, we use a converging convex lens. This starts bending the light rays inward before they even reach the eye's natural lens, pulling that focal point forward onto the retina. There are a couple of other really common structural hiccups too. Astigmatism happens when the surface of the eye has these varying, uneven curves, usually just due to age or a loss of lens power. Because the defect is on different planes, it requires highly specific cylindrical lenses to correct. Then there's presbyopia, which is essentially a total loss of the eye's accommodation power. As we get older, the biological lens hardens up and becomes inelastic. It just won't change shape anymore. The solution? Bifocal lenses, which essentially give the eye some mechanical assistance for both near and far distances. All right, moving to section 4, the mechanical lens camera. Engineering mimics biology. When you look inside a DSLR camera, you are essentially looking at humanity's deliberate attempt to build an artificial eye. The mechanism is brilliantly straightforward. Objects are placed in front of this complex converging lens system. Those lenses gather and bend the light, projecting it backward until it is captured on a light-sensitive surface, which historically was film, but today is almost always a digital sensor. To manage all that light, engineers came up with two distinct mechanical controls. First up is the aperture, which expands or shrinks to control the overall volume of light entering the lens. Second is the shutter, which is a physical curtain that opens and closes to control the precise amount of exposure time, literally dictating how long the light is allowed to physically touch the sensor. Grasping the distinction between these two is absolutely critical for understanding mechanical photography. And that brings us to section 5, biology versus machine, the ultimate synthesis. Putting millions of years of organic evolution directly alongside human engineering really puts things into perspective, doesn't it? You've got this soft, organic sphere filled with liquid and powered by blood and electricity, sitting right next to a rigid cylinder of glass, metal, and engineered sensors. Yet, functionally, they are trying to achieve the exact same goal using the exact same laws of physics. And this setup brilliantly illustrates just how closely the camera mimics the eye. Just look at the shared features here. Both utilize a converging lens system. One is biological, one is glass. Both project their data onto an image screen, the living retina versus chemical film or a digital sensor. Both systems, entirely due to the nature of converging light, project a real and inverted, meaning upside down, image onto that screen. And both control light volume with an adjustable opening, the expanding and contracting iris of your eye, and the mechanical diaphragm or aperture of the camera. But the differences in how they actually execute these functions are fascinating. To change focus, a camera has a fixed focal length lens that physically moves forward and backward inside the barrel, meaning the image distance is variable. Your eye is totally different. The distance from your lens to your retina is completely fixed. So how do you focus? Well, your eye literally changes the physical shape and thickness of its biological lens on the fly, varying its focal length. That's accommodation. Plus, while a camera takes simulated snapshots using a mechanical shutter, your eye is constantly capturing a continuous motion series, giving you a seamless stream of reality. It is pretty incredible to realize that every time you pick up a camera or peer through a lens, you are quite literally holding a mechanical mirror to your own biology. We learn the laws of light from nature, and we use them to build tools that let us see the universe. But it leaves us with a really compelling thought to end on. If human engineering already so closely mirrors our own biology today, what is the next evolutionary leap in optical technology actually going to look like? Will the lines between biological and mechanical lenses just blur entirely? Think about that the next time you snap a photo. Thanks so much for joining me on this explainer, and as always, stay curious.